Good morning, girls. Now we shall see what is D'Alembert's principle. Before seeing the D'Alembert's principle, we shall see what is the definition of virtual or infinitesimal displacement. Virtual or infinitesimal displacement of a system refers to a change in the configuration of the system as a result of any arbitrary infinitesimal change of the coordinate delta Ri consistent with the forces and the constraints imposed on the system at a given instant t. The displacement is called virtual to distinguish it from an actual displacement of a system occurring in the time interval dt during which the forces and the constraints may be changing. Principle of virtual work. Suppose that the system is in equilibrium, then the total force on each particle vanishes. Because if the system is in equilibrium, that means the system is not moving, that is in the stagnant position. So there won't be any force acting on the particle. So we can take that force as equal to 0. Whereas if you find out the dot product of the force with delta Ri, which is the virtual work of the force Fi in the displacement delta Ri, which will also vanish because that F is equal to 0. Since F is equal to 0, F dot delta Ri is equal to 0. The sum of these vanishing products over all particles must be 0. So here we said for each particle the value is 0. So for different particles, that is for n number of particles, if you are finding the sum of that F dot delta Ri, that will also be equal to 0. So virtual work done by all forces is equal to 0. The force Fi can be decomposed into the applied force and the force of constraint small fi, and the applied force is denoted by Fia. So any force can be written as the sum of the applied force and the constraint, force of constraint. So we may write that virtual work, that is sigma over I Fi dot delta Ri as, we can replace Fi by Fia plus small fi, and dot product with delta Ri is equal to 0. We can write that as two functions, that is sigma over I Fia delta Ri plus sigma over I small fi dot delta Ri equal to 0. Here we restrict ourselves to a system for which the net virtual work of the force of constraint is 0. So that means sigma over I Fi dot delta Ri to be equal to 0 we are considering. So if you replace it by 0 in the previous equation, then we get only the first term, that gives you sigma over I Fia dot delta Ri equal to 0. So we have the condition that for the equilibrium of the system, then the virtual work of applied force is 0, is that is nothing but sigma over I Fia dot delta Ri equal to 0. So this equation is called as the principle of virtual work. Whereas the coefficient delta Ri cannot be 0, that is Fia is not equal to 0 because delta Ri are not completely independent but are connected by the constraints. Now we shall see what is D'Alembert's principle. For a system of particles, the virtual work of the force of constraint vanishes, then sigma over I Fia minus Pi dot delta Ri equal to 0. That is, here Pi dot refers to the derivative of Pi with respect to the time t. Now we shall see what is the proof of that theorem. Let P1, P2, etc. Pn be the system of particles with position vectors r1, r2, etc. Rn, and the linear momentum P1, P2, etc. Pn, where these are the vectors, and P1, P2, the first one are the P1, P2, Pn refers to the position vectors. Okay. Let Fia be the applied force on the particle and small fi be the force of constraint. Then by Newton's second law, we know that the total force is equal to the derivative of Pi with respect to time, that is Pi dot. If you bring it to the left hand side, that gives you Fi minus Pi dot equal to 0. Now as usual, that is like that of the previous one, we are finding the dot product with the delta Ri. So here the system, the particle is in the system where the system will be in equilibrium, because here we are getting the left hand side is equal to 0. So in the place of Fi, here we have Fi minus Pi dot, that is equal to 0. So if you find out sigma over I Fi minus Pi dot delta Ri equal to 0, then we get sigma or I Fi minus Pi dot delta I equal to 0, whereas we can replace Fi by Fia plus small fi, and that gives you sigma or I Fia minus Pi dot. Here we are bringing that Pi dot to grouping with the Fia, and we are writing that the sigma or I Fi dot delta Ri as the second term. Now, like that of the previous one, here also we are restricting ourselves to the system for which the virtual work of the force of constraint vanishes. That means sigma or I Fi dot delta I equal to 0. So, if you make that to 0, then we will be left out only with the first term, that is sigma or I Fia minus Pi dot delta I equal to 0, which is known as D'Alembert's principle. Do you understand? Okay, thank you girls.